Okay, let's do a couple more examples of arc length. Should be relatively straightforward. Most of these we're just going to set up the integral. We're not actually going to go. We're not actually going to go the lengths of actually figuring it out. So let's go ahead and look at y is equal to 1/4 x squared minus 1/2 natural log x. And let's look at it from 1 to 2e. Okay. Well, I mean, it winds up being relatively straightforward. You know, you just put in y prime. Y prime winds up being 1/2 x minus 1 over 2x. And you can go ahead and get a common denominator if you would like. 1 over 2x. And so this winds up being x squared minus 1 over 2x. Then you would basically just evaluate it from 1 to 2e, 1 plus, and just plop in your y prime right here. And that should be that. Let's go ahead and some of these we may actually evaluate. We'll see what intrigues us as we move along. Let's go ahead and go from 2 to 8 of that one. Now it looks a little bit similar to one that we've already done, but this one actually is 2 terms, which basically makes the radicand a little bit more complicated, especially if it's something that we're seeking to do by hand. But let's go ahead and do y prime. Winds up being 1/2 x to the 1/2 minus 1/2 x to the negative 1/2. And all of a sudden this is looking a whole lot, this is looking a whole lot like the last one, right? And so we wind up getting x minus 1 over 2 root x. See the similarity? That's kind of neat. But from here, it really just winds up being the same thing in terms of just setting up the integral. 1 plus x minus 1 over 2 root x squared dx. Now, once you actually get done doing this, will it simplify down to something that can actually be worked out by hand? I don't actually really know. It'd be a neat thing to actually walk through it, perhaps, because some of these actually do, once you start fiddling with them in terms of the radicand, some of them do simplify into something that actually isn't really all that bad. And you've seen that before, problems that start out really, really messy and really intimidating and wind up being not really intimidating at all. Well, let's go ahead and do another one. So we have x cubed over 6 plus 1 over 2x, and of course some of us may want to actually rewrite it like that in order to make the differentiation a little bit more straightforward. And let's look at it on the interval from 1 to 2. Y prime winds up being 1/2 x squared minus 1/2 x to the negative 2. Wow, this is another one. Actually, this is from a different worksheet. Minus 1 over 2x squared, so that winds up being x to the 4th minus 1 over 2x squared. And we would set it up exactly the same way. Integral from 1 to 2. 1 plus x to the 4th minus 1 over 2x squared dx. And of course, calculator-wise, that would be an extremely easy one to do. Just pop it in and go from there. Now, let's go ahead and deal with one that's not going to give us a derivative that looks like that. Let's do y is equal to 2 arctan x. And let's do it from, closed interval, 0 to 1. Well, I happen to know that y prime is going to be 2 over 1 plus x squared. So then all we really have to do is go 0 to 1 of 1 plus 2 over 1 plus x squared dx. Okay. Well, I don't think that this actually winds up being one that works out rather nicely by hand, but certainly that's easy enough to plug into your calculator. Well, let's go ahead and look at something that's a little bit more quirky. How about that? Now, there are two ways that you can actually do this particular problem. Now, if it's e to the negative y, then we know that that can be y is equal to negative natural log x, right? Then all we would have to do is just transform that interval where when y is 0, x is 1, and when y is 2, it's e to the negative 2, or 1 over e squared. So actually this is in the wrong order. It would be 1 over e squared to 1. We could do this, but not every problem that's x in terms of y can actually be transformed rather easily into y in terms of x. So let's ignore this for the moment, and let's instead just do it with respect to y. And we should be able to do that. It's the same sort of idea. So instead of getting dy dx, let's get dx dy, and this winds up being negative e to the negative y. So we should be able to actually integrate it like that. Because all you're really doing is, instead of approximating the curve and transforming your delta x squared plus delta y squared, instead of transforming it like that into delta x squared plus delta x times f prime of x squared, you're transforming that into delta y times g prime of y squared plus delta y squared. And you're doing the same thing, you're just doing it with respect to y. And of course the slope would be, instead of rise over run, it'd be run over rise. So it wouldn't actually be slope, but it would still be an analogous rate of change. And that's why when you're dealing with this in terms of, with respect to y, you have it in terms of x like this, f prime of x squared dx, which of course is the same thing as 1 plus dy dx squared dx. But what you want to do is not this. Okay, that's correct if you're doing it with respect to x. What you want to do instead is go from c to d, which is the limits of integration along y that we usually use. That's how we, notationally differentiate it. dx dy squared dy, or g prime of y instead of that. Okay, so all we did was just differentiate with respect to the other variable in terms of y, plug it in, plug the limits of integration with respect to y, and plop a dy out there instead of a dx. Simple enough. Okay, let's do one more with respect to y, and then we'll sort of survey where we're at. Okay. If I have x is equal to 1/3 root y minus 3, and I want to evaluate the arc length from 1 to 4 along y. Now this is, you could do it by the product rule, but it's probably much, much easier to go ahead and distribute this. So it ends up being 1/3 y to the 3/2 minus y to the 1/2. Now, that actually should look somewhat familiar because it actually looks a whole lot like one that we did with respect to x, right? It looks a whole lot like this one. So we've actually already done this problem. We just did it with respect to x. It does, however, look a little bit different with respect to y, but that shouldn't actually fool us at all. Let's go ahead and do this very quickly. You know, and we can use x prime if we want. 1/2 y to the 1/2 minus y 1/2 to the negative 1/2. And if you're actually doing it in your calculator, you don't have to change that. I'm just merely in a habit of changing it since I'm used to doing things by hand. 2 root y, or y minus 1 over 2 root y. That's your dx dy, or your x prime. So you want to go from 1 to 4, 1 plus y minus 1, 2 root y squared dy. And that should be the end of it, okay? Now, we've run through quite a few examples. We haven't worked out a whole lot of them, and we haven't plugged them into our calculator because that comes later. Or you already know a lot of that, and of course reviewing that is always a good idea. But for the sake of this, I just wanted to run through a lot of examples in terms of how to set up the integral with respect to finding the arc length. Now from here, what we're going to do is in 8.2, I think it's 8.2, we're going to take that arc length and we're going to use that. We're going to use the arc length formula, which is of course 1 plus y prime squared dx. This, of course, right here represents the arc length, which is going to be important if you then want to take it and instead of finding the volume of a solid of revolution, you can use this plus a few more components to find the surface area of a solid of revolution. And that's going to be the next application of integration that we're going to look at in 8.2. Okay?